Hello students, this is the leftover part of our discussion on risk and return. In this screencast, I will discuss the mean variance approach to the topic because this approach is generally used in the context of portfolio management. We will construct our discussion around an economic agent who seeks some utility maximizing portfolio given that he or she desires to put a part of his or her savings in a set of common stocks. In this approach, we assume that the utility of a decision taker depends only upon two factors: the expected return on portfolio and the risk that the portfolio carries. The first step to this end is to understand the choice set from which the decision taker makes his or her optimal choices. This choice set is known as the portfolio possibility frontier. So, our first task is to understand this frontier, and we have the question that how this frontier is obtained and what are its features. Though we work in this presentation with only two assets, the discussion could be extended to any number of assets and without any alterations in the main conclusions. Before we go into the discussion of portfolio, let's first try to recall the risk and return that might be associated with any one investment or an asset. See that in this example where I have used this table, there is an asset which may give a rate of return of 15% or of 10% or 5%, depending upon that whether the economic situations remain good or average or bad, and that the probability that the conditions remain good is 30%, so that this is 0.3, and that not good not bad 0.4, and that the conditions may remain bad is equal to 0.3. So we want to find the expected return on this investment or on this stock and the risk that might be associated with it. So here see that I have written the formula for expected return. You might be able to recall this: probability time times the return in a particular situation, and we sum all these up. So for example here I have 0.3 multiplied by 0.15, similarly 0.4 multiplied by 0.10, and finally 0.3 multiplied by 0.5, 5% rate of return, and in this way I am able to get on this asset an expected return equal to 10% or 0.10. Now let's see that how we find out the variance of return on this asset. See that I have written this formula for variance. You may be able to recall this from your previous courses in statistics, and I have used the same to compute the variance of this asset in an example, and it is like see that the summation of the probability of the jth condition times the return in jth condition minus the expected return, and then that we are squaring all these differences, and when we do that, so we obtain the rate of return the variance equal to 0.0015. Variance has to be positive, and that similarly the standard deviation is the positive square root of the variance. Let's now turn to the portfolio problem. Here we have defined some symbols. See that by Rij means that the return on ith security when J is the state of nature, and that Si is the share of wealth or savings that has been directed towards the purchase of asset I. Similarly, we will be using Rp to define the return on portfolio, and sigma p to define the standard deviation of portfolio. In the two asset case, see that I have drawn this table where this first column is giving me the return on asset 1 when the states of nature are good or average or bad, and similarly the returns on asset 2 when the states of nature are good, average and bad. These are still the probabilities of these states of nature. And if we compute the expected return on only asset 1, so we know that how we will be doing that. We have already seen that earlier. So let's say that this is the expected return on asset 1 and this is the expected return on asset 2. Similarly, if we compute the standard deviation using the previous discussion on asset 1 and assets 2, we will be getting like sigma 1 as the standard deviation of asset 1 and return on asset 1 rather, and sigma 2 as the standard deviation on of return on asset 2. Here we are going to assume the following. The first one is that R1j is less than R2j. That is that in every situation, good, average or bad, we will be having the corresponding entries of column 1 less than the corresponding entries of column 2. And this means that we will have the expected return on asset 2 greater than the expected return on asset 1. Assuming the normal conditions where we expect a positive relationship between risk and return, we will be maintaining that the standard deviation of asset 2 is greater than standard deviation of asset 1. And then see that we have written down the statement for the expected return on portfolio. By 1, the probability of the state of nature 1 multiplied by the proportion of the savings or wealth that you have tied to asset 1 multiplied by the return on asset 1 when the state of nature is 1 or good, and similarly is true about each of these entries. See that because we have only 2 assets, so whatever are our savings, we will be dividing those savings in these 2 assets. So S1 is like mentioned is the proportion of the saving tied to asset 1, and S2 is the proportion of our investment in asset 2, and so these two proportions must add to 1, so that I can write from here that S1 it can also be written as equal to 1 minus S2. If we compute this expected return on portfolio, see that in this second equation I have taken this S1 out as a common from this first parenthesis, and that S2 out common from this second parenthesis, and in this way I get this formula for return on portfolio. Though the return on expected return on particular asset is constant, but see that the return on portfolio is not a constant. It will be depending upon the values of S1 and S2. So moving from one value of S1 to another value of, actually will be like going from one portfolio to another portfolio, because there are infinite combinations of S1 and S2, so there we can make infinite combinations of portfolio, and so there are like infinite values of expected return on portfolio as well. If there had been more than 2 assets, then this would have been the formula for the return on portfolio, summation of SI E of RI, and that This is like S1 ER1 plus S2 times ER2 plus S3 times ER3 and so on up till Sn times SRn, where n is the n is the total number of assets. In the case of two assets, see that I have rewritten this formula here. Expected return on portfolio. Then the next thing is to see the variance of a portfolio. Again, remember that while variance of each asset is constant, the variance of portfolio will keep on changing as S1 and S2 changes. Here I have given you for refreshing your memory the formula where two standard where two random variables are involved, random variable x and random variable y, and suppose that we are talking about the variance of the sum of these two random variables. So this is like the formula that you might have seen in your basic statistics courses. I have rearranged this formula a little bit by opening these brackets in this format, and see that when I do this, it is like in the form of a square, a plus b whole square, and so I can open this using that formula. So this will be like this is the variance of x, and similarly the y minus expected value of y square is like the variance of y, and this 2 times e of x minus ex and y minus ey actually is the covariance. So that is something that you may be able to recall from your previous courses in statistics, and I have written it a little bit differently in the form of sigmas. So this is the variance of x and y equals to the variance of x plus variance of y plus 2 times covariance xy. And see that we modify this formula a little bit to write down the variance of our portfolio, because shares are involved here. So I write down sigma square p, that is the portfolio variance, equal to s1 square sigma 1 square plus s2 square sigma 2 square plus 2 times s1 s2 multiplied by the covariance between the returns on assets 1 and assets 2. That is then has been converted in this form, where I have introduced a correlation coefficient here. Recall that correlation is between any two random variable is equal to covariance divided by the standard deviation of one random variable multiplied by the standard deviation of the other variable. So I actually have used this equation to replace covariance, and so by cross multiplying this, and so this was that we get the formula around here involving correlation coefficient here. And then I ask the question that what is going to be the standard deviation, the variance of this portfolio when these two assets are perfectly positively correlated, so that the correlation between these two assets is equal to 1. The return on the correlation of the return on these assets is equal to 1. In place of row 1 2 1, so that correlation between the return on these two assets is equal to 1. So this equation becomes like this one, and then see that we have this quadratic equation, and I can write it as now as s1 sigma 1 plus s2 sigma 2 whole square and then taking the square root of it, I get the standard deviation of this portfolio equal to S1 sigma 1 plus S2 sigma 2, where S1 and S2, as mentioned, are the proportion of your savings going to asset 1 and asset 2 respectively. I have in the next step solved the variance formula, the standard deviation rather, into S1. So in place of S2, I have put 1 minus S1, and then see that I have solved that equation for standard deviation of portfolio for S1. And after doing that, in this equation for expected return on portfolio, I am putting this formula in place, this in place of S1. So see that this is still S1 times ER1 plus S2 times ER2, and then if I take the derivative of this equation with respect to sigma p, so I get this equation, and this is like 1 over sigma 1 times 1 minus sigma 1 minus sigma 2 times ER1, and similarly 1 over sigma 1 minus sigma 2 times ER2. And if I take 1 over sigma 1 minus sigma 2 common, so see that in the bracket I will be getting E of R1 minus E of R2. And now see that the term in this bracket is going to be less than 0, because ER2 is greater than ER1, as we have assumed earlier. So this is your ER sigma 2 rather, and so this is negative or less than 0. Side by side, see that sigma 2 has been assumed to be greater than sigma 1, so this means that this is also less than 0, and so we have that the derivative of the expected return on portfolio equation with respect to the portfolio standard deviation is greater than 0. So this is something that I have plotted here, and in this equation as a positively sloped line, and see that if I put S1 equal to 1, so this means that here we will be getting 1 minus 1 equal to 0, and in that event we will have this portfolio standard deviation equal to sigma 1, which is this point. Then see that if in this equation if I put S1 equal to 0, so this means that this is equal to 0, equal to 1, so this means that this is equal to 1, and similarly this ratio is equal to 1. This goes out, becomes equal to 0, and I get ERP equal to ER1, and so I have this point on this line where this is like stating that I am allocating all of my savings in asset 1 only. Similarly, if I put S1 equal to 0, so then this sigma p will become equal to sigma 2, and similarly this ERP will become equal to ER2, and so I'll be able to get this point. And then in between this slope is constant, and so these are the choices that are available to the investor when the investor is like changing the composition of his asset holding, like from this point to this point, starting with S1 equal to 1, and here becoming S1 equal to 0. So all savings in asset 2, here all savings in asset 1, and that this is the in-between question and the in-between situation. And so like I told you that we can have infinite possible portfolios by varying these S1 and S2 values, but then that as a result we will keep on moving along this is constant slope line, and this is what that is the shape of the portfolio possibility frontier when we have two assets and that the returns on these assets are perfectly positively correlated. So what does this remember that this also means that while this possibility is available, but this is inefficient or inferior to the one which is lying vertically above this. So as far as the portfolio choices are concerned, not only those choices are available to the individual or the investor that are lying on this portfolio possibility frontier, but that all these choices are also available, but then they are inefficient. But then side by side see that we are calling this a frontier for the reason that these are the choices that are not available. So you may call this line as a portfolio possibility frontier or set of efficient asset combinations when the assets are perfectly positively correlated to each other. So this is the case when the two assets are perfectly positively correlated to each other. Next, let us look into the possibility where rho 1 2 is equal to -1, so that the return on two assets are perfectly negatively correlated. Because of this we get a minus sign now here, and that as a result see that now we can use the a minus b whole square formula to write down the equation for variance, and then when we want to find out the standard deviation we need to take the square root on both sides, and when we do that we obtain these two roots. This is the first root and this is the second root, and then see that because standard deviation has to be positive, we know that none of this equation is satisfied for all combinations of S1 and S2. So we have to define for example the range of S1 that has to be satisfied for standard deviation to be positive. You can plug into first equation, for example S2 equal to 1 minus S1, and solve for S1 after writing the condition that S1 sigma 1 minus S1 times sigma 2 greater than equal to 0. You can solve that equation for S1 and you will find that S1 has to be greater than sigma 2 divided by sigma 1 plus sigma 2 for this root to be positive. And that if you look at the maximum side that S1 can have, and that it has to be equal to 1, and when S1 will be equal to 1, this S2 will become equal to 0 and we'll get sigma p equal to sigma 1. So for the first root, this is the legitimate range for S1, and for S2 you need to subtract S1 from 1, and then you will be able to find out the value of S2 as well. Similarly, for the second root, again you will have to find the range, and that range will be lying between 0 and sigma 2 divided by sigma 1 plus sigma 2, and this is something that you can do by yourself. But then see that if in this root we have sigma 1 equal, S1 equal to 0, then this means that sigma p will be equal to sigma 2, and so this is the lower limit of S1, and then that the upper limit is again being defined by sigma 2 divided by sigma 1 plus sigma 2. Finally, see that if we put sigma p equal to 0, then actually S1 either from this equation or that this equation will become equal to sigma 2 divided by sigma 1 plus sigma 2. So this is the value of S1 when portfolio standard deviation is equal to 0. In the next step, I have solved these equations for S1. So for example, this is the equation for S1. Again, remember that this I have done after eliminating S2. And this value of S1 must be lying in this range that we have already described. And similarly, for the second root, I have this value of S1, formula in fact for S1, and that this formula should be lying between 0 and sigma 2 divided by sigma 1 plus sigma 2. So let's start with the first root. I insert the value of S1 into the expected return equation of the portfolio, and when I do that, so the expected return on portfolio can be written in this format. See that this is S1 plus 1 minus S1, and in this way, now see that expected return on portfolio again has become a function of portfolio standard deviation, and when I take the derivative of this equation with respect to portfolio deviation, so see that this is something that I get. And because we have been seeing that expected return on security 1 is less than expected return on security 2, this term in the parenthesis is going to be less than 0. This outside the parenthesis term is positive, and then this means that this derivative actually is negative. So if we are using this particular value in this equation, that is when we are using the first rule, so we get negatively sloped relationship between expected return on portfolio and the standard deviation of the portfolio. Now in the next step, I have put the variance of standard deviation of portfolio equal to 0, that is sigma p, and when I do that, this is the equation I get, and see that I can see now that this expected return on portfolio in fact is greater than 0, because all these terms are greater than 0, and this is happening when we have sigma p equal to 0, that is the standard deviation of portfolio equal to 0. This means that this equation will have a positive vertical intercept if I am plotting the expected return on the vertical axis and variance along the horizontal axis. So see that this is what that I have done here. The negatively sloped line which is having expected rate of return equal to ERP hat, which is the one when standard deviation of portfolio is equal to 0. This is something that we just saw. So this ERP hat actually is this thing, sigma 2 divided by sigma 1 plus BR1 plus sigma 1 divided by sigma 1 plus sigma 2 ER2. So that is the vertical intercept. And see that in this equation, if I put sigma S1 rather equal to 1, then this will become equal to 0, and my return on portfolio, expected return on portfolio, will be equal to the expected return on the security 1. Similarly, if I put S1 equal to 1 in this first root, then see that I will be getting sigma p equal to sigma 1. So if I put S1 equal to 1, my expected return is equal to ER1, and that my portfolio standard deviation is equal to sigma 1. So this is this point that I am able to get. And then if I am having S1 equal to sigma 2 divided by sigma 1 plus sigma 2, the minimum range for this particular root of S1, so then I will be on this, so on this intercept. So this is going to be the equation of the return on portfolio when I am using the first root of the variance formula. Then see that I also have written down ERP hat in between these two limits, ER1 and ER2, and this is something that I want to show that why this is happening. What I have done here in this equation is that from the equation of ERP I have subtracted ER1, and when I do that and simplify it, so I get this end result, and this is like saying that this is greater than 0, which indicates that the expected return on portfolio is greater than expected return on security 1 when sigma p is equal to 0, or when I am using S1 to the extent of sigma 2 divided by sigma 1 plus sigma 2. So we then know that this ERP hat has to be greater than ER1. Similarly, you can repeat this exercise by putting in this equation ER2 rather than ER1, and when you subtract from ERP ER2 on both sides, you will be able to see that the result will be less than 0. Whatever is the final equation, you will find that it will be less than 0, and so I have defined this intercept between ER2 and ER1. So this is an interesting conclusion, that even with zero risk, I can construct a portfolio from these two securities such that S1 is equal to sigma 2 divided by sigma 1 plus sigma 2, and by doing that I will be able to get a return, expected return, which will be greater than the expected return on security 1. So this is the story of the first root. Similarly, in the second step, I have used this second equation for S1 into this expected return equation, and when I put it here, S1 equal to sigma 2 minus sigma p divided by sigma 1 plus sigma 2, etc. When I do this here, then see that the derivative of this equation with respect to sigma p now is greater than 0, and that is like saying that the second root will give me a positively sloped portion of the portfolio possibility frontier. Side by side, if I put sigma p equal to 0, see that I again get this same equation, which is like telling me that when the standard deviation is equal to 0, expected return on portfolio is greater than 0, with S1 equal to sigma 2 divided by sigma 1 plus sigma 2. And note that this equation actually is the same as we had obtained in the case of first root here, and so the two roots will have the same vertical intercept. And then see that when I put S1 equal to 0 here, for example, so this means that ERP will become equal to ER2. So when S1 is equal to 0, my expected return will be equal to ER2. And as per this second root, when I put like for example in this equation S1 equal to 0, so this means that S2 is equal to 1 and sigma p becomes equal to sigma 2, and so I have the point here, which is like telling me that when S1 is equal to 0, I have expected return on portfolio equal to ER2, and that the standard deviation is equal to sigma 2, and that the portfolio comprises of only security 2. Now, given that we have plotted both of these equations, the result for the first root and the result for the second root, see that when we analyze this portfolio possibility frontier, these two legs, in fact, of the portfolio possibility frontier, we can see that this is something, this vertical intercept actually is something that is superior to all these points, and this means that when this opportunity is available, though these points are available on the portfolio possibility frontier, yet the person will want to find himself or herself at this point where risk is equal to 0, and where expected return actually is greater than ER1. So moving from this point where S1 is equal to 1 and expected return is ER1 and risk is equal to sigma 1, moving from this point towards this vertical intercept, see that it is actually is reducing the risk and increasing the expected return, and this means that this point actually is superior to all these possibilities. Similarly, see that and in this way, remember that there is no trade-off. Rational behavior will demand that we should not be lying on this leg of the portfolio possibility frontier. Then see that when we use this portion of the portfolio possibility frontier, there is a sort of trade-off that if I want a higher return than ERP had, then I'll have to assume a higher risk. So this is something that is the second leg of the portfolio possibility frontier, and while this collectively is defining the portfolio possibility frontier, see that this is the leg which is defining the efficient portion of the portfolio possibility frontier. If for example the person is willing to assume this risk, it is not rational to be on this leg, and rather the person would want to be on this leg, and this means that the person would want to have S1 between sigma 2 divided by sigma 1 plus 2 and S1 equal to 0. So this will be the range which will be defining the efficient part of the portfolio possibility frontier. So this is something that is happening in the case where the securities are negatively perfectly correlated. In the going, see that we have defined the possibility that the portfolio possibility frontier may have some inefficient combination. So this entire is the portfolio possibility frontier when the two securities are perfectly negatively correlated to each other, but this red portion actually is defining the efficient portion of the portfolio possibility. Let's now turn to the case where the returns on two assets are totally uncorrelated to each other. See that I have rewritten here the general equation for the portfolio variance, and that in this formula, if I put rho 1 2 equals to 0, then the equation becomes sigma square p equal to s1 square sigma 1 square plus s2 square sigma 2 square, and if we take the square root on both sides, so we will be getting the standard deviation of this portfolio, and this is the expression for that. And see that if we put rho 1 2 equals to minus 1, we will be having this term, that is the left hand side term, and if we put sigma 1 2 rho 1 2 equals to 0, we'll get this right hand side term of this weak inequality that I have written here. These left hand sides and the right hand side of these expressions are actually defining the upper and lower limits to the standard deviation. And see that in this case, when we add 2 times S1, S2, sigma 1, sigma 2, we are able to get this right hand side, and if we subtract from this amount 2s1, s2, sigma 1, sigma 2, we get the left hand side of this equation. So this means that standard deviation of the portfolio in which the returns on two securities are totally uncorrelated to each other will be lying between these two limits. In this graph, I have plotted all the three possible portfolio possibility frontiers. Recall that this blue is the portfolio possibility frontier when rho 1, 2 is equal to minus 1, and this is the portfolio possibility frontier when the rho 1, 2 is equal to plus 1, and here I am claiming that this is going to be the shape of the portfolio possibility frontier when rho 1, 2 is equal to 0, and that in order to see that we will have to find out the value of S1 from this expression, and then we can put that value of S1 into the expected return equation and define expected return then as a function of portfolio standard deviation, and then we could take the derivative of expected rate of return in that equation with respect to the standard deviation of portfolio to see that what is going to be the sign of that derivative, and if we investigate the first derivative and second derivative of that equation, we will be able to ascertain that this is going to be the shape of the portfolio possibility frontier when rho 1, 2 is equal to 0. That is a very tedious job, and to avoid that, I have created this example where I have put some values of S1 and S2. See that we start with S1 equal to 0, gradually increases these values to finally make S1 equal to 1, and as S1 increases, S2 decreases, so that S2 finally becomes equal to 0 starting from 1. In this third column, I have written down the product of S1 and S2 because it appears here. Now notice that if either of S1 or S2 is equal to 0, for example in this case as well as in this case, this last term in this left hand side under root will be vanishing, and similarly it will be becoming 0 in this right hand side under root as well, and this means that when either of S1 or S2 is equal to 0, then the standard deviation of the portfolio in which the returns on securities are perfectly negatively correlated will be equal to the standard deviation of the portfolio where the two returns are totally uncorrelated to each other, and that will also be equal to the standard deviation of the portfolio where perfectly positively correlated. And see that it is because of this reason that in this graph all the three portfolio possibility frontiers have these same terminal points, like here as well as here. So here S1 is equal to 1 and here S1 is equal to 0, and so see that in all the three cases we have ERP equal to ER1, sigma P equal to sigma 1. Similarly here ERP equal to ER2 and sigma P equal to sigma 2. So this is your horizontal axis which is plotting portfolio standard deviation. And then in between you can see that as this product S1, S2 varies, the product initially increases, it will reach a certain maximum, and then it will start decreasing to become equal to 0. And this is like saying that this difference or say distance between the portfolio where the returns are not correlated to each other at all, and where the returns are positively correlated to each other. See that this distance initially will be increasing. For some values of S1 and S2, this distance will be becoming maximum, and then it will start decreasing. And so we'll have this particular shape of the portfolio possibility frontier in the case where the correlation between the two securities is equal to 0. And this is something that I have drawn here in this particular graph. And this graph then tells us that in this case where rho 1 2 is equal to 0, again the portfolio possibility frontier will have a portion which will indicate a negative relationship between standard deviation of the portfolio and the expected rate of return on portfolio. And see that in this segment the relationship between the portfolio standard deviation and expected return on portfolio is positive. And I have drawn this vertical line to show you that on this portfolio possibility frontier there is a particular portfolio where the standard deviation will be at its minimum portfolio standard deviation, and that I have associated with it an expected rate of return, portfolio return, and I have labeled it as E of RP dash. And we want to find out the portfolio which will give us this minimum standard deviation, and associated with this that particular is expected rate of return. In order to do that, I have written this equation again here. In fact, equation here. This is your standard deviation of the portfolio when the two securities are uncorrelated to each other. This is the equation that I had already written in the earlier part here. And when I solve it, like by putting in 1 minus S1 in place of S2, so this is the final equation that we get, and I have used this equation here in this case. And then see that the square root on both sides gives me the standard deviation of such portfolio, and when I take the derivative of the standard deviation with respect to S1, I am able to get finally the value of S1, which is equal to sigma 2 square divided by sigma 1 square plus sigma 2 square, and which is like saying that this is the share of my savings that I should be putting in security 1 when the two assets are totally uncorrelated to each other, such that when I do that, my variance will be at its minimum. Recall that this is the standard optimization problem, taking the derivative of this function with respect to S1 and equating it to 0, and then solving it for S1. So this is what that I have done here, and in this way I can find out the value of S1, and that value of S1 then could be subtracted to find out the value of S2. And once I have been able to find these values out, I could find the minimum variance portfolio in the case where the two assets have correlation between them equal to 0 in terms of their return. Now, given that this is the shape of the portfolio possibility frontier when the two assets are uncorrelated to each other completely, this is then defining the efficient subset of the portfolio possibility frontier, and this is defining the inefficient subset of the portfolio possibility frontier. Of course, this means that when this choice is available, so no investor will want to see himself or herself on this segment of the portfolio possibility frontier. So this is the efficient portion of the portfolio possibility frontier in the case where the correlation between the returns on two assets is equal to 0. So coming back to this first graph, see that if I have the correlation between these two assets such that the correlation is between -1 and +1. So this was the case where correlation was equal to 0. If the correlation between the returns on two assets is between 0 and 1, so this means that we will be having a portfolio possibility frontier which will be having this same sort of shape but a little bit inside or towards this portfolio possibility frontier, which is associated with row 1 to equal to 1. And similarly, if the correlation between the returns on two assets is between 0 and -1, so this means that this will be a little bit more away from this particular portfolio possibility frontier or nearer to this portfolio possibility frontier. In any of the case where the correlation is between -1 and +1, we will be able to find the shape of the portfolio possibility frontier. It will definitely be having a negatively sloped portion, a positively sloped portion, and a sort of minimum variance portfolio associated with it, which we could define using the same procedure that we have written here. Here in this last expression, I have used this equation to find out the standard deviation for any correlation between -1 and +1, whatever that correlation is. If I take the derivative of this equation with respect to S1 like we did in the case where the correlation was equal to 0, so I actually will be getting this formula for S1. So for any correlation between -1 and +1, this formula actually will be giving me the value of S1, which will be defining the portfolio with the minimum standard deviation, and then we will be able to see that what is the associated expected rate of return. See that if in this formula I put row 1 2 equal to 0, so that the correlation between the returns on two assets become equal to 0, this formula will reduce to sigma 2 square divided by sigma 1 square plus sigma 2 square, something that we have already seen. In this last graph that I have plotted here, see that I have superimposed on this portfolio possibility frontier the indifference curves of a risk averse person, and given that the person is expected to maximize his utility, we could imagine that the person would choose a portfolio such that the indifference curve, one of the indifference curve becomes tangent to this portfolio possibility frontier, and this then will be defining the optimal portfolio for the person in question. And see that this equation this condition could be written in this form: the slope of the indifference curve is the marginal rate of substitution, because along the vertical axis we have expected rate of return, and along the horizontal axis we have portfolio standard deviation. So this is the MRS between portfolio standard deviation and expected rate of return on portfolio. And similarly, The slope of the portfolio possibility frontier is the marginal rate of transformation. It could be described in this way, and so we can say that this equality rather, should be satisfied to ensure that we have identified the utility maximizing portfolio for the person in question. Now, remember that in case where the person is risk neutral, then the indifference curve of this person will be becoming linear, and when this is the case, see that this will indicate that the utility maximizing portfolio will be here where S1 is equal to 0. And this is the case for the risk lever. We keep in mind that risk lever indifference curves could not be drawn in this fashion, because if you are doing that, you are saying that return is bad and risk is good, but this is actually not the case with the risk lover person. We say that he actually likes both of them, risk and return, and so see that moving from this point to this point, he is willing to accept more risk for higher return, and both these conditions takes him to a higher indifference curve. To keep in mind the shape of the indifference curves in this space of expected portfolio rate of return and standard deviation, that they are not like this one where you were describing y as a bad good and x as a good, because return is never bad, and that this is the case where the person is risk level. So let me write it down here, E of RP, and so we have been able to define the three cases for risk level, for risk neutral person, and for any person which is risk averse, and that in this case this tendency condition will be satisfied, and in these two cases, either of these two cases, we will have the corner solution with S1 equal to 0 here, S1 equal to 0 here. So these two persons, because this one is risk neutral and because this is risk lower, so these two persons will keep all of the savings in terms of security 2, where the standard deviation is equal to sigma 2, and where expected rate of return is E of R2. Similarly is true for this case as well. So this is the situation where the two assets are either uncorrelated to, either totally uncorrelated to each other, or the correlation is between -1 and +1, somewhere between -1 and +1. And remember that in any of these cases where correlation is between -1 and +1, we will have an efficient portion of the portfolio possibility frontier and an inefficient portion of the portfolio possibility frontier, and that for the risk averse person, you can see that this tendency condition will only be satisfied in this portion, efficient portion of the portfolio possibility frontier. So this is the case where the correlation between the returns on two assets is between -1 and +1. Finally, let's consider the case where one of the two securities is risk free, and see that this is how our equation of expected returns on portfolio changes. We are assuming here that security 1 or asset 1 is risk free, and that asset 2 has more than one possible return associated with it. So this expected return on portfolio is equal to the proportion of savings allocated to asset 1 multiplied by the certain return on asset 1 plus the proportion of savings allocated to asset 2 multiplied by the expected rate of return on asset 2. And then see that given that this is the formula for variance in the case where two assets were involved, if asset 1 is risk-free asset, then this means that sigma 1 becomes equal to 0, and so we have variance of portfolio equal to S2 square, sigma 2 square. Taking the square root on both sides gives us the standard deviation, and I use this standard deviation to find out S2, and I subtract S2 from 1 to get S1, and that then I plug into this equation of return on portfolio these values of S1 and S2, and so I am able to get expected rate of return on portfolio as a function of standard deviation of portfolio. And see that when I take the derivative of this equation with respect to standard deviation of portfolio, so I get this result, which gives me finally this equation, which is greater than 0 because ER2 is greater than R1 and sigma 2 is positive, so everything in parentheses is greater than 0, so this difference, and that this entire term becomes greater than 0. So this means that this is a linear equation with a slope equal to 1 over sigma 2 times the difference of the expected rate of return on security 2 and the certain rate of return on security 1, the risk-free security. Also see that if in this equation I put sigma p equal to 0, then this term will be becoming 0, and sigma p becomes 0 means that sigma 2 will be cancelling, and I will be getting expected return on portfolio equal to R1, which is the vertical intercept of this equation, and so I have put this thing here, ERP equal to R1 with sigma p equals to 0. And that given this linear expected rate of return function of sigma p, see that I have been able to draw this efficient portfolio possibility frontier for the case where one of the security is risk-free and the other security is the risky security. That if I put S1 equal to 1, then this means that I am allocating all of my savings to the risk-free asset, and if I put S1 equal to 0, then this means that I am allocating all of my savings to the risky asset, and that along this portfolio again the tangency condition must be satisfied for the risk-averse person, so that the marginal rate of substitution between expected rate of return on portfolio and standard deviation of portfolio is equal to the marginal rate of transformation again between expected rate of return on portfolio and standard deviation of portfolio, and that it seems as if the conditions do not change a lot when we move from the case where there are two risky securities to the case where there is one risky and one risk-free asset. The only thing that happens is that this portfolio positive frontier is a positively sloped straight line, and that it will be lying between this intercept and S1 equal to 0. Given this, now look into the case where we are doing a little bit of different things, and it is that I am mixing the risk-free asset with a risky portfolio, Let us say that the risky portfolio consists of two risky securities. Call these risky securities as security A and security B, so that if we think in terms of security A, I could write that the return on security A, actually expected return on security A, will be equal to ERA, and that its variance will be equal to sigma A. Similarly, we can define the expected return on portfolio B as ERB, and ERB, and that the right ERB, and that the standard deviation of security B, let it be equal to sigma B, and let's assume further that E of RB is greater than E of RA, and also that given our previous assumption, we can also write that sigma B is going to be greater than sigma A. Then see that between these two risky securities, when we obtain the portfolio possibility frontier, it is going to look like this blue frontier. We have taken only the efficient portion of the portfolio possibility frontier, and see that this is the point where we have allocated our savings to only the portfolio of risky assets. Call this portfolio E1, and then connect this point rather, with this intercept R1 to obtain this ray, and then see that wherever we are on this ray, it will be representing a proportion of saving is going to the risk-free asset, and the part of the proportion of the saving is going to the portfolio being represented by E1 of the risky assets. And that as we move towards this vertical intercept, this means that the proportion of the saving that is going to risky portfolio is decreasing, and the proportion of the savings going to risk-free asset increase. And this ray is representing the linear combination of the risk-free assets and the portfolio of the risky assets being represented at point E1. Now see that if we move from point E1 to point E2, we have another portfolio, and if we are here, then this means that we have allocated all of our savings to the portfolio of risky assets, and that if we connect this point to the vertical intercept, we again get a ray, the red ray this time, and see that any point on this ray will indicate the mixing of risk-free security with the portfolio being represented by E2. Note that this ray that is giving us the combination of risk-free security with the portfolio represented by E2 is dominating all these combinations which are available on this lower ray, and so this means that all the combinations on this red ray are relatively efficient to all these choices which might be available on this lower ray, because for the same amount of risk, this lower ray offers a smaller expected rate of return relative to this red ray, and so this means that when these opportunities are available, they will not be chosen. And similarly, see that when we move from point E2 or portfolio E2 to this particular portfolio, let us call it E star, and when we connect portfolio E star with the with the vertical intercept, then we get this blue ray, and this blue ray then is giving us all the possible combination of portfolio E star and the risk-free security. So if we are here, this means that all savings are allocated to risk-free security, and when we are at E star, then this means that all the savings have been allocated to the portfolio of risky securities, which is made up of these two securities, A and B. Note this particular characteristic of this blue ray, and it is that this ray is a tangent at this point to this portfolio possibility frontier that we have made using these two risky securities. This means that I cannot draw another ray with a higher slope, and such that ray will have any connection with this portfolio possibility frontier of the risky assets. So in the presence of these two risky assets, and in the presence of this risk-free assets, given that we have this portfolio E star, see that this segment of this ray from this vertical intercept to point E star is defining for us the efficient frontier, and that this means that the person will be choosing any point along this segment of this efficient frontier. For example, here, if the person is risk averse, one of his or her indifference curve will be tangent to this efficient frontier at this point, and then we can conclude that still the optimal portfolio selection requires that marginal rate of substitution between expected rate of return on portfolio and the standard deviation or risk is equal to the marginal rate of transformation, and that is and that it is not going to change if we have a risk-free security. What changes, see that as a result of risk-free security, is that these points which were efficient in the absence of risk-free security, after risk-free security becomes available, these points on this particular frontier becomes inefficient, because for the same risk, on blue, this light blue frontier is offering higher rate of return. So in place of being here, the person will want herself or himself at this point, and in fact, if this is the indifference curve, the person would want to see that along this portion of this efficient frontier, the person is able to reach the highest possible indifference curve. And that is one part of the story. Now let's look at the same graph from another point of view, and it is that suppose that this frontier of the risky securities actually is not made up of two securities, rather it is made up of all the risky securities that are available in the market. So suppose that this is the case, that this frontier that we have drawn here, in place of representing only two securities, it is representing all the n securities that might be existing in the market, n risky securities. And given that we have obtained this frontier, which we may call market frontier, market asset frontier, or market security frontier, because it includes all the securities and or assets that are available in the market except the risk-free security, and that still, in order to obtain the efficient frontier, the same thing will be required, that we have to locate the ray which will be starting or emanating from this vertical intercept and will become tangent to this market frontier at some point. This point, or say this particular uh, portfolio, let's call it E dash, is known as the market portfolio, and that in this event, this efficient frontier that we so obtain is known as the capital market line, sometimes written as capital market line, market line rather. And that in this case again, see that the optimization conditions will remain same, that optimal portfolio will be the one which satisfies the condition that marginal rate of substitution is equal to the marginal rate of transformation. Now, one more thing that we want to add here is that suppose that the person is at this point, then this means that part of the a proportion of the savings have been invested in this portfolio, and proportion of the savings are going to the risk-free security. And uh, saying that the person has purchased a risk-free security actually describes the person as a lender, as if the person has lended some money or a portion of his or her saving at a risk-free rate of interest. And so we can say that these are the choices which are available to the person when the person can act as a lender in the money market. And that given that a person can act as a lender, see that the person can also act as a borrower, and this becomes evident if we like extend this line more rightward like this. So there is a possibility that the person might be finding himself or herself at such a point, but then again this is a tangency point, and that see that the person, if he or she had been here, so this means that he or she had been investing all of his or her saving in this portfolio being represented by E dash, but so that the proportion of saving going to this particular portfolio becomes 1. But then when we move from this point to this point, then this means that the allocation of the savings or proportion of savings going to this particular portfolio is greater than 1. It would have been 1 if we had been here. It would have been less than 1 if we had been down here, and it definitely will be greater than 1 if we are in this range. So a person can act as a lender, or the person can act as a borrower. The difference between, or the distance between this point and this point will then be defining the extent of borrowing, and the distance between point E dash and this point will be defining the extent of lending, borrowing. Sorry, that this is lending and this is the extent of borrowing. And I have drawn this graph here again. This red is the frontier that or efficient part of the frontier, in fact, that we have obtained by using all the securities that are available in the market. So see that from this point to this point is lending, and from this point to this point is borrowing. Note that one thing is true for lenders and borrowers, and it is that for both of them the optimality conditions remain same, and it is that marginal rate of substitution for lender must be equal to the marginal rate of transformation. Similarly, the marginal rate of substitution for the borrower should also be equal to the marginal rate of transformation. And given this means that this entire equation must be satisfied. marginal rate of substitution for lender equals to marginal rate of substitution for borrower equal to marginal rate of transformation. Finally, note the last point, and it is that for market clearing in this simple model, it is required that all borrowings must be equal to all lending. So there will be distribution of different types of lenders in this segment, and there might be distribution of different types of borrowers in this section. But then what we are suggesting is that for market clearance it is required that sum of all lendings must be equal to the sum of all borrowing, and when this happens we say that the asset market is clearing. So this is the final conclusion for the mean variance approach, and it allows us finally to see that while the optimality conditions remain same when the risky securities are mixed with risk-free security, the effect of including a risk-free security is that the efficient frontier is redefined. See that in the absence of risk-free security, this was the efficient point, but after a risk-free security becomes available, so you see that this becomes inefficient relative to a point which is vertically above this point, and so this portfolio is efficient in the presence of risk-free security, and that similarly is true about portfolios like this. So see that this portfolio now, though it was previously on efficient frontier when there were only risky securities, but see that with risk-free securities this point is dominated by this point which is lying vertically above this portfolio. And so this is the end of our discussion on the foundations of the mean variance approach to the risk and uncertainty.